All right, so tonight I cover sections 4.1, and we'll do a little part of 4.2. I don't think I'll do the whole thing. I think save some of that for class next week. Suppose you had this. So this is a discrete distribution. I don't know what it's about. All I know is those are your things you can actually have happen to you. That should be 0.3, 0.6, 0.9. Yep. If I want to find the average value of things that could happen here, for instance, on a 5-sided dice that's obviously heavily weighted, for instance, I want to find the average, or what we often refer to as the expected value. So we'll write it this way: the expected value is another name for long-term average. It's another way of saying this is if you play this long enough, this is where things should end up. Okay. Expected value of a function is pretty straightforward. It is simply the sum in a discrete distribution. It's the sum of the x's times their probabilities. Okay. And that's it. And so what we're saying here is that the expected value is simply this. No, sometimes this is also referred to as the expectation. I don't really care for that. It just sounds weird. You could also think of it as the mean or the average. Whenever you see expected value, a lot of times you'll also see the Greek letter mu. That is as a variable that means average. So in this case here, it'd be just 1 times 0.1 plus 2. 0.6 plus 3, 0.05 plus 4 times 0.2 plus 5, and then 0.05. Okay, it's 0.1. It's plus 1.2. 0.4, 0.48. 1.68, 1.78. That'd be your expected value. By the way, it doesn't shock me because most of our probability is down this lower end. So it makes sense that the average would be down there somewhere. Okay? It's pretty easy to do when you have that situation. In general, when you have an expected value of x, that is exactly what you do. It'd simply be x times, oops, that's not a sum, that's an integral. Okay, I goes 1 to n. Now, if that was for a discrete or for a continuous distribution, it'd be x times your PDF. Integrate it from a to b, from wherever the f of x exists from. So, for instance, yeah, right there ought to be a PDF. Okay, let's see if that's true. So it's 1/6, and then it's x squared over 2 plus 2x from 0 to 2. So that'd be 4 divided by 2 is 2, plus 4 is 6. 6 divided by 6 is 1. So that's true. Now, if I said I wanted to find the expected value of this, it'd simply be 1/6. I'd put an x right there because it's the expected value of x. And then I would just integrate across that whole thing. And so if you distribute that out as x squared plus 2x. So it's x cubed over 3 plus x squared from 0 to 2. And what is it? 8/3 plus 4, 1/6. And so that'd be like 12/3, be 20/3. which is 20/18, which is 10/9, which is 1.11111. Yeah, that is the expected value of x in that problem. Okay, makes sense that it's a skosh bigger than 1 because 1 would be right here, and clearly there's a little more on this top side, so it's going to be somewhere in there. That would be the average value. Okay, or again, the expected value. Now, interestingly enough, a fella could say, well, listen, I want, what is the expected value of, I don't know, 2x? Wait, 2x? What would I do there? It's literally this. Instead of putting an x there, it would be equals, if it was a discrete distribution, it would be 2x times the probability of x. Okay? And you're like, well, can I pull that 2 out front? Of course you can. Okay? Well, what if it was expected value of 2x and it was a continuous? Well, then of course it'd be 2x times your probability, and you of course you could pull the 2 out. And so, and if you did that, of course, one would notice that in both instances, why this 2 times that is going to give you what? This right here is the expected value of x. So it's going to be 2 times the expected value of x. Well, what do you know? It's twice as big as it was before. That's right. Not a surprise at all. So in general, your book writes it this way. Okay? If I want the expected value of g of x, that is, g is a function of x, so x squared, 2x, 5x plus 9, whatever it is going to be equal to the sum, I goes 1 to n, of g of x times my PDF, my probability function, right? And then, of course, this is the exact same thing if it's continuous. Just like that, right? Piece of cake. Now I know what you're thinking. What if I had a joint distribution? That is, what if x and y were jointly varying, right? Well, then I could have the expected value of g of x and y. In other words, could be something like x plus 2y. That is a function of both x and y. If I wanted the expected value of x plus 2y, I would simply take and do the integral, if it was a continuous distribution, of this g of x and y times my f of x and y. This part right here, dx, dy, whatever, this part right here is your PDF, right? And if you put this part in front of it, you're going to see that you will get the expected value of whatever that function happens to be. Ditto if you are doing a discrete distribution. If you're doing a discrete distribution, it's the exact same thing except it's double sums instead. Okay, pretty easy to do. Nothing too hard about them there. So I'd like to do a couple here. Turns out, if you've ever watched the game Roulette, I've never played it, but it looks interesting to me. There are 2 green spaces. They are 0 and 0, 0, and then there's 1 to 36. The number's 1 to 36. Every other one is black. So you can do odds or evens. You can do black versus red. Okay. Whenever I play this game and I make a $1 bet, okay, I expect to have something happen. Well, first of all, I expect to lose money. Okay, I expect to lose money. So when I play this game, it's simply going to be, well, look, what could happen? Let's say I bet on the number 17. Well, if I land on the number 17, okay, I am going to be paid back my bet plus 30 plus. Come on, Jay, you can get this off the top of your head. I have to think about it for a second. Hang on. Yes, you get your bet plus $35. So if you bet $1, you get your bet plus $35. You get $36. There's a 1 in 38 chance of landing on that. Otherwise, you're going to win nothing. Right? Now, interestingly enough, when it comes to gambling or insurance, which is just gambling, it is the sum of the x's times the p of x's. This is true. 100% accurate. Minus, however, the cost to play. So in this situation, it'd be 36 times 1/38 plus 0, obviously, minus the cost to play. Well, I bet $1 to play this game. So 36 divided by 38 minus $1 turns out to be about a nickel. In other words, every time I play, I expect, when I bet on a single number, I expect to lose a nickel on average every time I play. Well, how does that work? Well, it means this. If you played all day long, you would win about, give or take, 1 out of every 38 times. And you'd win $36. But in the meantime, you would have lost, basically, you would have lost you'd have lost $35 in essence. And so when it was all said and done, if you divide it out, you'd have lost, I should have done out of 100. Well, whatever. Anyways, you'd end up losing more than a nickel. But if you divided it out by the number of games you played, you'd end up losing about a nickel per game. Okay? I will do a little demo of that in a minute. Now, I love this game because it doesn't matter what bet you choose, it's always the same answer. It's interesting. That's why I think it's fun. So, turns out that if you were to bet on odds, for instance, there are 18 odds. Or, sorry, there are 18 odds out of 36. That's pretty good odds. I didn't mean to make fun there. So if you win, you get your dollar plus another dollar. You win $2. If you lose, you win nothing. Oops. And there are 20. No, there's 18 out of 38. 18 out of 38, which is 20 out of 38. I knew that looked familiar. Okay, anyways, it's the sum 2 times 18 out of 38 minus the cost to play, which is $1. And I lose a nickel again. And it doesn't really matter how you play this game. Which one you bet on, you always bet the same. Someone else might say, well, wait a minute. What if I bet more money? Wait, what do you mean if you bet more money? You mean if you bet $5? That's right. Suppose I did a $5 bet. Well, that's cool. So what I'm going to end up doing is instead of winning my dollar plus, instead of winning my $5 plus instead of winning my dollar plus $1, I'm going to win my $5 plus $5 more dollars. So if I did that, it would be 5 and 18 out of 38 and 0, 20 out of 38. If you do that, that's like 90 out of 38, but the cost to play was $5. And when you do that, you will see that you end up losing. I can't do math anymore. Alright, so 90 divided by 38 minus 5. Yep, and then I hit that little diamond enter there. Oh, I looked at that. I expect to lose negative $2.63 every time I play. Well, wait a minute. $2.63. Wait, divided by 5 is what? Oops. Somewhere I made a boo-boo. I made a boo-boo. Dope. I win my $5 bet plus Judas Priest. I win what I bet plus what I bet. So last time I won $1 plus the $5 I bet. This time I'm going to win my $5 back plus $5 more dollars back. That's $10. Judas Priest, I got a problem. Alright. It's 180. Let's try that again. Yeah, it's 0.263. There we go. I lost 26 cents roughly. Okay, well, what is 26 cents? 26 cents is 5 times as much as this. In other words, the expected value of 5x is equal to 5 times the expected value of x. Okay, this kind of stuff also works nicely for insurance. I only talk about life insurance. Other stuff's too weird. Life insurance, you win or you lose. You're dead or you're not. Okay, there's no, well, I got in a wreck, but I'm not going to claim it because my insurance rates will go up. That's stupid. So if I die, I win the bet. Okay, So $100,000. That's how much my life insurance policy is. That's what I'd win if I die. Okay, and then let's say there's about this much chance that I croak today, which is pretty good. That's pretty good odds, really, that I croak. It's not really good for me. I don't like that. Yeah, 10. That's what I thought. Okay, so then 0, and then of course the rest of the percentages would have to go right here, right? So my expected value would be equal to 100,000 times 0.0001 minus the cost to play. Well, what do we call that? Well, in insurance we call that a premium. And so what will end up happening is this. The insurance company will say, listen, I want to make this much money in profit on each policy. This right here would be the profit. For you, it's going to be negative. For the insurance company, it's going to be positive. So watch this. Suppose I told you that we charge this fella $100 a year for $50 a year for this policy. Okay. Well, this part here is 10. 10 minus 50 is negative 40. The customer loses $40 on average for every one of these policies. Okay. In other words, you buy this policy over time, over the next, let's say, 10 years that you got this policy for, you would expect to lose the $40. Okay. The insurance company is going to make that $40 in profit. That's how it works. Again, on average, nobody won $40. Nobody lost $40. Okay, your premium is $50. You either lost $50 because you didn't die, or you won $100,000, which is not really winning because you're dead. Okay, that's the game. All right, they're kind of fun. They're kind of neat. Pretty easy to do. Here's a couple of nice little book problems here. For instance, if a dealer's profit in units of $5,000 on a new automobile can be looked up as a random variable having this density function. Okay, it wants to know this. Find the average profit per automobile. Well, literally it's saying find the expected value of X. Oh, I'm going to die tonight. Pardon me. Well, good news, I have my insurance paid up, so if I kick the bucket, it's not a big deal. Okay. All right, there it is. And so, cool, from 0 to 1. And so this ends up being 2. What are you doing, you idiot? It's x squared over 2 minus x cubed over 3. 0, 1. And that's 1/2 minus 1/3 times 2, which is it's 1/6, so it's 1/3. So it's 1/3 of a unit, and the units were in $5,000 increments. So 1/3 of 5,000 is roughly $1,600, or thereabouts. Okay, that's kind of handy. Here's another book problem. I like this one because it's tricky and it may fool you. It should not, but it may. Oh, whoops, don't need that one, right? So here are the probabilities that you land any in those spaces there, okay? 0.1, 0.05, 0.02. Okay, and 0.1, 0.35, 0.05, 0.03, 0.1, 0.2. Okay, now if I wanted to find the expected value of this thing, the expected value of for instance, let's just do a nice easy one, the expected value of X. Well, what do I mean by that? Well, the expected value of X is add up to, if I add this direction, that's 0.35, 0.5, Somebody can't add too good. What? That's 0.07. That's 0.17. I don't add very good. 0.17. 0.5. Goodness sakes. And this would be 0.35. Okay, there's a problem here. Oh, that's because this is a 3. That makes me a little happier. Holy mackerel, I can't read my own handwriting. Clearly this better up to 100%. And now it does, finally. Whew! So the expected value of x would simply be 1 times 0.17 plus 2 times 0.5 plus 3 times 0.33. Expected value of y would be similar, except, different, because it'd be 0.23, 0.4, 0.5, 0.27, right? So then that would be 1 times 0.23 plus 2 times 0.5 plus 3 times 0.27, right? And it's pretty straightforward. What if I wanted to do x plus y? The expected value of x plus y, the expected value of x plus y, well, what would that equal? Well, it would equal, let's see, 1 plus 1 is 2 in here, yes? So it'd be 2 times 0.1. 1 plus 2 is 3. 3 times 0.05. Plus 1 plus 3 is 4, so 4 times 0.02. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. 2 plus 1 is 4. 5. If you add that up, that would be the expected value of x plus y. That's all it means. Okay? And I'll do one more that's a joint distribution just for a good time. Ooh. Yeah, that one looks fun. Oh, but it's even. I can't do that. That's an odd to me. Yeah, I say, here we go. So, number 26, it says you've got f of x and y is equal to 4xy, 0 less than x, and y less than 1, 0 elsewhere. Okay. Awesome. Find the expected value of z, where z is equal to the square root of x squared plus y squared. Okay, so what I'm looking for is this. But what I really mean by that is, what is the expected value of x squared plus y squared? And what do I mean by that? What I mean by that is do the double integral. All right, so x is greater than 0. So I'm sorry, it's x greater than 0. So 0 to infinity. And I draw the picture the right way? I did. And y is less than 1. So so okay. It just still looks funny. Okay. Well, I think that's right. There we go. So, something's just weird about it. So, I'm going to do the antiderivative first. Something that's still weirding me out just a little bit. Oh, wait. Yeah, something will screw with that. So I need to look over I'm not reading the book correctly or something there. Something's weird. I knew I was reading something wrong. See, what it's saying is, and I hate this about your book. This is so dumb. X's and Y's are between 0 and 1. You with me? X's and Y's are both between 0 and 1. Instead of the normal human just going, hey, listen. Why wouldn't you? I don't know. That's just what it is. I knew there was a problem when I looked at my antiderivative and went, no. Put infinity in there, we got problems. So I can go back in there now and do it right. And your answer is 0.243. That's the expected value of x squared plus y squared square rooted. Okay? That's all that means. It's pretty easy to do. We'll do some other examples of things like that later on. As I mentioned the other day, we talked about, listen, hey, you got x here. X is distributed some length. You got y, that's a different kind of thing. It also has a distribution. When we marry them together, you get x plus y, right? That becomes a new thing, which also has some new variation to it. And we're going to talk about that. What is the average of that new married thing? So we'll come back to this, this idea of expected values. Okay, it's pretty easy to do. So it's pretty easy to do this stuff. It's not hard at all. The next thing we're going to talk about a little bit, but I'm not going to finish it up, is the idea of how do you find variance, okay, and the standard deviation, okay. So the variance, which will be written like this, is the expected value of, and then I'll write it like this. Quite honestly, there's about a million ways to write it. This is how your book does it, which is the actual correct way if you're talking about it from this point of view. If you're not talking about it from this point of view, it doesn't make any sense at all to do it this way. Okay? Now, let's think about what this means for a minute. Okay? If you were to FOIL that out, you get x squared minus a 2xm. And then, what do you get there? Minus the mean squared times f of x. Okay? Well, wait a minute. What is another name for the mean squared? Another name for the mean squared is... the name for the mean squared is the expected value of x and then squared. And then, wait a minute. Check this out. Check this out. Wait, before I do that. Hold on. Don't do that yet. Don't do that. Well, yeah, okay, go ahead and do that. Now, let's go ahead and FOIL this mess out, shall we? So you end up foiling this out, and you're going to get x squared f of x minus, I'm going to pass the sums through while I'm at it, minus 2 x f of x, and I'm going to pull the mu out front because the mu is just a constant, okay? And then plus, this is also a constant, sum of f of x's, okay? Well, wait, the sum of the f of x's is by definition 1, right? Right? If you sum up the function from a to b, right, the whole thing it sums to 1. Now check this out. This guy here by definition is the expected value of x, or if you prefer the mean. So what I have here is I have 2 means squared, or if you prefer, and I do, I think in this case, 2 expected values of x squared plus this becomes 1 expected value of x squared. And then here you're left with, this would be literally the expected value of x squared. Because by definition, that's what that means. So what I get is it's the expected value of x squared minus the expected value of x squared. This is going to be written in either case. But notice that you're going to find the mean first. Let's say the mean was 5. You just throw it in here. You take x minus the mean, whatever that is, square it, and times by that, and then you're done. Jay, give us an example. Hey, I'd love to. Here is the number of children, number of boys you can have in a 4-kid family, obviously. right? Now, it turns out that the average is, you're not going to believe this, the average is a half. How'd you do that, Jay? Love to help. So 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16 is 0. That's 4. 12 is 16. And 12 is 28. And 4 is 32. 32/16 is better known as 2. So if I want the standard deviation, I'm going to do this. It's the expected value of x, whatever our x's are, minus the mean squared times probability. Okay? So in this case, it's going to be 0 minus 2 squared times 1/16 plus 1 minus 2 squared times 4/16. 2 minus 2 squared 6/16 minus 3 or plus 3 minus 2 squared times 4/16 plus 4 minus 2 squared times 1/16. Let's try that. 2 squared is 4. It's 4/16. I'm going to leave it like that if you don't mind. 1 minus 2 is 1 when you square it, I mean. So plus 4/16. 0. 1 4/16. 4 minus 2 is 2. Squared is 4. 4/16. Okay, what are you going to get here? What are you going to get? 16. What do you get? You get 16/16, which is better known as 1. Okay? Ta-da! And so that's that. Now the standard deviation by definition is the square root of the variance, the positive square root of the variance. So it's 1. We'll talk more about standard deviation in upcoming days, like a little bit more about how it means. That's it. Notice I could have done it this way. I could have also done it the way I was talking about doing it before. Remember I said before it's the expected value of x squared minus the expected value of x squared. Well, what that would mean is I take 0 squared times 1/16 plus 1 squared times 4/16 plus 2 squared times 6/16 plus 3 squared times 4/16 minus the expected value, which was 2 squared. So here I'm going to get 0. I'm going to get 4/16. I'm going to get 4. I'm going to get 24/16. Get 9. I'm going to get 36/16. And 16/16. Minus 4. And so it's 28. And I don't know. It's got 40, 76. You get 80/16. AKA 5, right? And then so you get 5 minus 4 is 1. Ta-da! It's the same. Okay? Makes you happy when it works out. It's kind of neat, kind of a cool deal. Now, is that also true for the standard deviation if you have a continuous? Of course it is. It's x minus mu squared times your probability. Okay? Make sense? And so you're like, oh, okay, well, can it work the exact same way? Yeah, this thing still foils out the same way every time. And you'll end up with always the expected value of x squared minus the expected value of x squared. And what does that look like? So if a person has already done this guy here by definition is the expected value of x times your f of x. All right? Whatever this is e of x. So whatever you get, square it. This part here would be, this part right here would be this guy. So whatever you get, just do your deed. If this came out to 7 and this came out to 3, it'd just be 7 minus. Well, that couldn't work. Sorry. Let's say this one came out to be 2, for instance. So you get 7 minus 2 squared is 4 is 3. This would be your variance. It's that easy. Okay. Let's do one off the homework or something similar to it. Now, this week, I'm going to stop right there. I'm not going to do joints this week in the video. I want to save those for class time. I want to do some of those in class this week because I think they're kind of fun. And it's kind of interesting, I guess. So, yes, there's a nice one. Right. So, if you have f of x equal, well, 1/3 e to the minus x over 3, x bigger than 0. And ask you for the mean, aka the expected value, and it's going to equal this. It's going to ask you for this fella, which of course we know is the expected value of x minus mu squared. Okay, so let's try this. By definition, this will be the expected value of x, right? Let's try it. Now I'm going to go ahead and put in a million or something, okay? Because I know it's going to converge at the top end. And so you're like that. If you hit diamond enter, you'll see what it is. You'll see that the answer is, da-da-da, come on. Oh, you piece of garbage. Oh, it's undefined. It's not undefined, you piece of garbage. Okay, so let me back up the train a little bit here. Escape, clear, clear, clear. Alright, so 1/3. There you go. Integral. Must have dropped my negative somewhere. No, I didn't. No, I didn't. I see it. Anyway, x times e to the negative x divided by 3. Yeah, there's your antiderivative. Okay? Now, what happens to this beast as x goes to infinity? Well, you'll end up with, I'm going to jot that thing down. So you have to do a little bit of negative x. All right, well, remember that could be written as negative x plus 3 over e to the x over 3, right? If you put infinity in there, who gets bigger faster, x or e to the x? Well, e to the x does. So the limit of this guy as x goes to infinity is 0. So it's going to be 0 minus, and then if you put a 0 in there, you're going to get negative 3 and negative 3. So negative 3, and then of course times 1/3. So the answer is, when you do this problem, the answer is 1 is my expected value. Okay? Now if I want the variance, I literally just do 1/3. So the variance, 1/3 integral, and then we do x minus the mean squared times e to the minus x over 3 dx. By the way, one could see that if I was a horrible, mean, awful teacher, I would make you do all these integrals by hand. You wouldn't learn anything, but you would get to do integrals till you're blue in the face. Wouldn't that be fun? No, it wouldn't be fun, Jay. Which is why I don't do it. So there's your antiderivative, negative x squared plus 4x plus 13. Over e to the x over 3, right? Right. Oh, I just realized something on that last problem. You see in that last problem there was a 1/3 there, and then when I was done I times it by a 1/3 again. I shouldn't have done that. The answer should have been just a 3 right here, which means this is wrong. Let's try that again. Negative x squared plus 9. Oh, okay, that's hot. Now, again, at the top end, the limit of this, obviously the denominator is getting bigger faster, so it's going to be 0. Minus, you put a 0 in there, you're going to get negative 9 over 1, so you're going to get negative 9. So your variance is going to come out to be 9, which means your standard deviation is going to be 3. Okay. Now, again, I could have done it differently. I could have done it this way. I could have done the expected value of x squared. And I show this because a lot of teachers will teach it this way instead. I don't really care. You find a way that makes you happy, and we'll roll with it, okay? So if I found this guy first, let's do that. And it's pretty easy because all I got to do is just get rid of this dumb 3 right here. Boom. So now you see I got that gross mess over e to that. So it's negative x squared plus 6x plus 18 over e to the x over 3 from 0 to infinity. Obviously at the top end it's 0. At the bottom end it's going to be 18. It's going to be negative 18. That makes sense? Negative 18. So 18 is your answer. 18 is the expected value of x squared. Now I need to take the expected value of x and square it. Well, the expected value of x was 3. So if I square that, I get 9. 18 minus 9 is 9. And that is just another way of finding that guy right there. So I'm going to leave the joint stuff for in class on Wednesday night. And we'll also talk a little bit about covariance as well. So this will get you started. All right, bye-bye.